Welcome to 2.1, Vector Methods in One Dimension. First, a couple of things just to quickly go over. First of all, the term vectors in of itself. Remember, these have both direction and magnitude. So something like a force would be a vector because you would have a direction in which that force moves, but something like temperature would not be. When we talk about vectors having both direction and magnitude, they can then exist collinearly, which means they exist on the same plane or dimension. Now that could be kind of like an east-west plane or a north-south plane or even some sort of diagonal plane, but they are in the same line with each other, which if you got multiple ones collinearly, you add the two together and you get a total result. That is the resultant vector, the total of adding things together. So vectors are usually drawn as arrows, and the length of the arrow represents that magnitude. Whereas the arrow is always pointed in the direction that the vector is moving. So you got both magnitude and direction represented with the single arrow. Now, obviously, sometimes these vectors cannot be drawn on our papers to the same amount, and so what we've got is cases where we will need to use a scale. And so if we take a look at this first example, drawing a vector of 5 meters to the right, we might use a scale of, let's say, 1 centimeter is the same as 1 meter. In which case, 5 meters to the right would be drawn as 5 centimeters. And so we'll draw our line 5 centimeters in length. And then top it up where the arrow is pointing to the right. This next one with 20 meters going down, well, again, 20 meters may not be the most appropriate length to draw on a page. So we might say 1 centimeter is equal to 10 meters in real life. If that is the case, then what we'll do is get our ruler nice and set here in an up-down position, and this will be 2 centimeters in length. And because it's going down, we draw our arrow pointing down. For the last two, we're going to use 30 kilometers north and 150 kilometers to left. For these, we'll use a scale of 1 centimeter is equal to 10 kilometers. So with this first one, this 30 kilometers north would be represented with a line 3 centimeters long heading to the north. The north is usually indicated on the top of the page, so it'll look something like that. Last one, again, same scale, 1 centimeter is equal to 10 kilometers. Now this is moving to the left. I'll get my ruler straight. So we're going to draw this line 15 centimeters in length, but it's going to be pointing to the left. Right? So each one of these, the length is representing of the magnitude, how strong it is, the direction. Each one of these vectors has its own scale because we're drawing 4 individual vectors, but when we draw them in the same diagram, they should have, in fact, the same scale. So when we combine vectors, we're usually do them in what we would call a tip-to-tail method. Now, a vector has 2 parts. An arrow has 2 parts. So if we drew one arrow to the right, this part here would be the tip, and this would be the tail. So if we're doing 2 vectors, adding them tip to tail, we've got one vector to the right and a second vector also to the right. Notice that the tail of this one, the one in blue, is next to the tip of the black one, the one that we drew first, and so it's tip to tail, right? Whereas if we were adding a third vector, we'd add it to the tip of the second one. But if one is going to the right and the other one is going to the left, because it's difficult to superimpose, we put them right next to each other, but again, we've got the tip of the first one next to the tail of the second one. Now, while there are several methods we use, the one we're going to be using is we're going to add them together with being mindful of the signs. And so let's take a look at what that would mean. We're also going to draw them out using a scale of 1 centimeter is equal to 1 meter in each case. So we got a man walking 5 meters to the right and then 3 meters to the right. So we take that plus 5, right? 5 to the right, right meaning positive, and we're going to add to that positive 3, which means we should get positive 8. And so this would represent a positive 8 meters if we're adding them together. Drawing out that, our first vector I'm going to put together here in blue, 5 to the right, with the scale of 1 centimeter is 1 meter, means 5 meters. Okay, and then we'll do a second vector from there, and it's going to be 3 meters, also to the right. A little bit wonky there, but hopefully you'll forgive me. And so what we see is this drawing is in fact 8 centimeters in length. What happens if he's walking 5 meters to the right and then 3 to the left? Well, we've still got that plus 5, and we're going to add to that, but 3 to the left is negative 3, which would result in a positive 2 meters total. And if we were to draw this out to scale, we still have our 5 to the right, and then we're going to add to that 3 to the left. And so that will look something like this. And so what we see here is a result that would be, in fact, 2 centimeters in length. That is representative of 2 meters. So if we were to draw the resultant vectors, and I'll do that in green, this one here has a resultant of 2 meters in length, represented with this 2 centimeters, going again to the right, where that first one, the resultant vector, again we'll do in green, comes along like this, and notice it is 8. So the green is what we call the resultant. The resultant, the result of adding those two vectors together. Now, in some cases, it is going to be necessary to draw things tail to tail. But this is always when we have two objects and we're doing a comparison. So if we were to take a look at, let's say, two men coming apart, one's traveling to the right at 5 meters per second. Traveling to the right 5 meters, it would look something like this. Using the same scale as before. And then we're going to draw a second one. Three centimeters in length. Notice the difference is a total of 2 meters as a difference, but we will draw them out tail to tail. Again, this is because there's two men, so black is representing man 1, blue representing man 2. Similar thing where one is going to the right, the one 5 meters to the right, and 3 meters to the left. Again, we're using the same scale as before. And so it would look like this. Notice we do have the same spot and we're adding them tail to tail. Again, that is because we have two different objects, not the same object. So lastly, if we were to find actual distance using just the vector diagram, what we've got here is an example where we want to find out the speed of the individuals that they're separating. Well, we see here that this is approximately 1.7 centimeters. Well, let's pick something a little bit more visible. 1.7 centimeters. And the other one is approximately 2.8 centimeters in length. And so this person going to the left is traveling at a rate of 3.4 meters per second, and that is because the scale is 2 meters per second for every centimeter. This other person is traveling at a rate of 5.6 meters per second. And so they are separating from each other at a rate of 9 meters per second. Now, we also could see that they are separating a distance of 4.5 centimeters length, tip to tip, which brings us to a total of that 4.5 centimeters multiplied by 2 also gets us the 9 meters per second. Remember, in all our solutions, you're going to need to include your answer, but as well as your logic for finding your answer. Whether that be adding the vectors together or whatnot, needs to have that together. Make sure you're always using proper physics conventions, and answer should be rounded to the same number as the digits in your question. Thanks for watching.